This 12-node polygon is the basis of SHDCCP codex utilization. This is a visualization of the compression steps, from 12 nodes to 1. The master octave represents all 12 foundation nodes. The next step is a 2-to-1 compression down to 6 diametrically opposed nodes. This is the first harmonic octave, forming a cube. These 6 nodes go through another 2-to-1 compression to the next 3 diametrically opposed nodes, forming a triangle. The last compression cycle translates to one central point. This is the orientation quaternion. This cyclic pattern compresses all 12 outer nodes in the master octave in 3 steps of 2-to-1 compression to form a central point. Let's go back to the start and project these nodes onto a 3D cubic lattice. The 12 edge nodes compress to the 6 face center nodes. The 6 face nodes are synthesized into a single center point, a 7th central node. This 7th central node acts as the compressed total of the 6 prior nodes translated into 3 more nodes, forming a tetrahedron. The tetrahedron is crucial because its vertex points act as the 4 components of the central quaternion, allowing orientation, but also allowing chirality. Chiral systems encode history and path into its final result, not just a simple sum. This is the key to lossless compression. We can project these rotation functions in a 3D simulation and see how they form patterns as we increase and decrease phase rotations per quadrant. Each quadrant represents either the 12-node, 6-node, 3-node or 1-node compression amplitude at that point in the compression cycle. The higher the rotations per cycle, the more accurate a curve trace we will get. This really helps amplify accuracy when projecting or decompressing back out from a central quaternion with compressed neural symbolic data and codecs. The higher the precision per rotation per cycle you can get, the codec size available grows exponentially. While lower phase rotations are easier to manage, leading to less possible branches in the hyperbolic toroidal path, we are only simulating a 1 Planck length compression cycle around a proton. Increasing the nodes increases the data wrapping compression around the central node per cycle, or in this case our compressed quaternion representing the whole chain of steps in 4 conceptualizations. With enough of these nodes, we can simulate the collapse of longitudinal waves around a central mass point. This collapse shows geometric projections, exactly as needed to perform these simulated lattice structure transformations and compression twists. It's the third part in the full wave cycle. It just needs multiple context perspectives to measure.